Lecture 50, Diffusion, Effusion, and Real Gases. These are some definitions there you should know. What is the difference between diffusion and effusion? What is the same about both? Well, diffusion is read off the definition, the process whereby a gas spreads out through another gas to occupy the space uniformly. So, this is the movement of one gas through another. Like the scent of a perfume or a candle making its way through a room. It's the molecules that make up that scent diffuse through the air. Effusion has a strange definition. Seems like it's kind of a very esoteric thing, but it's the process in which a gas flows through a small hole or aperture. Movement of a gas through an aperture or small hole. And this, again, it seems kind of an odd definition to worry about, but the effusion of gases through apertures, small holes like that, allows us to separate out gases by their mass, and it also is something that we need to think about when we're considering leaks in systems, or when you're trying to remove one gas from another. Effusion comes into play, so it's important. So let's use this. And then what's the same about both? Diffusion and effusion are affected by molecular weight. So the molecular weight of the molecules, the larger they are, the slower they move. And diffusion and effusion are affected by temperature. The more, or the hotter something, the higher the temperature is for a system, the faster the molecules are moving, so the faster they're going to move either through a gas or through an aperture. So there's the things that are the same and things that are different. Find the RMS speed for a nitrogen molecule. I think I changed what I had there, so a nitrogen molecule, and we have to have a temperature. I didn't put it in here, but we'll say 298. Same for the uranium hexafluoride. So the RMS speed, the root mean square speed, is U, and that's 3 RT over the molar mass. So we have R is the gas constant. It's the same one that we've used, but it has different units of measure, so we have a different number for it. And this is 3, and R is 8.31 joules per kmol. And temperature is going to be 298. But the molar mass for nitrogen, that's 28 grams per mole. But we're going to be using 0.0280 kilograms per mole. And so it seems odd that we do that, but remember joules, this is kilograms times meters squared per second squared. So if we, and the reason that's, we're using joules here, so we need to know that it's made up of these units. And the reason we're using joules, well, let's see, once we do the calculation out, I'm going to expand this whole thing out. So we have 3, this is 8.31 kilograms meters squared per second squared times K times mole. So a lot of units there, 298 Kelvin. And then 0.028 kilograms per mole. So if we put the gas constant into these new sets of new set of units, we can cancel this. K cancels, kilograms cancel, and we're left with meters squared per second squared. And the square root, that gives us meters per second. And that's what we're after. We're after that speed. So we do this out. 3 times 8.31 times 298 divided by 0.028 take the square root, and we end up with 515 meters per second at 298. That's very fast. Think about a college classroom, like many of you are in during your lectures. That's about 15 meters across, 15 or 6. So a nitrogen gas molecule at 298 Kelvin, if it was allowed a free path and it just bounced off the walls, it would go back and forth across the room 34 times per second. That's pretty quick, but so you should get used to that. Most of these molecules are going to have a very high speed. Now you do it for uranium hexafluoride. We've just been using this so much that I remember that it's 352 grams per mole, or 0.352 kilograms per mole. The reason you like to use uranium hexafluoride is that it is a gas. It has to make it into a gas, it has to be a little higher temperature, but it has a high vapor pressure, so we could expect that there'd be some uranium hexafluoride at 298 Kelvin floating around. And I've left it in these units, but the kilograms in there, no need. Now that you see why we use the joules, oops, this is 352, oops, sorry, 352 kilograms. You should know that it cancels the same way each time, and we end up with meters per second. No reason to break it up every time. And I get 145 meters per second. And that seems reasonable. It's such a heavy molecule that it should travel slower, but that's still fairly fast. We're talking about it's still bouncing back and forth across the room 10 times per second if it were allowed free reign through, and there's essentially a vacuum inside the classroom otherwise. All right, calculate the rate of the ratio of fusion rates of helium and neon. So the rate of a fusion of helium is proportional to 1 over the square root of its molar mass. And the rate of a fusion of neon is proportional to 1 over its molar mass. Hopefully I have enough room here. So it's equal, say that you make this equal if we have some proportionality constant. We'll just call it K. Well, we don't know what K is, and we don't know if it's related to if it's different for each compound or each species. So if we take the ratio of these rates, then the K drops away. This is what we've done with a lot of our gas laws, and by having two different systems or two different species, we can get rid of this extra value we really don't want to worry about. So if we take the rate, I'm just going to make it shorthand, rate of helium over rate of neon. Let me check, make sure I'm on. Yep. Then remember, it's helium, it's 1 over, so the molar mass of helium is going to be on the bottom, and its K value would be on top. Let's just put in there. And the rate of neon, since it's on the bottom, that would push its molar mass, the square root of its molar mass, onto the top, and its K value would be on the bottom. Assuming that they're constant for each gas, these would cancel, and then we end up with a very simple formula now. And if we put in our numbers for neon, it is 20.2 grams per mole. And here you might say, well, why didn't we change to kilograms per mole? Feel free to. And it just, in this case, it was important up for the other problem because we had that gas constant. We've deleted our gas constants here, so you can make this kilograms per mole, and then that'd be 0.0202. This would be changed to 0.004. You'd end up with the same value. So in this case, since there's no reason to change the units, I wouldn't do it. You can bring, since it's the square root over a square root, bring them both under the same sign. and then we solve it, and this comes up to be 2.25. It's a ratio, it's just a number. What that tells you, though, is that helium, the rate of effusion of helium is 2.2 times faster than the rate of neon. So very shorthand there, but the rate of effusion of helium is 2.2 times faster than neon. So we go on to the next problem, and it asks, it takes helium 4.11 seconds to effuse through an aperture in a container. Under the same conditions, how long will it take the same amount of neon? Well, if we hadn't done this first problem, we'd have to determine the rate first. And so you'd take helium and neon, find their molar masses, put them under the in the formula we just did. But we know that helium is 2.25 times faster. And not the speed, it's RMS speed, but effusion rate. So I'm just shortcutting it here, but since I'm saying it out, I think it's okay. So since helium is 2.2 times faster, 2.5 times faster than neon, that means neon should be 2.25 times slower. So if we take 2.25 times 4.11, that gives us seconds. 4 times. Then 9.25 seconds. So neon will take 9.25 seconds to effuse under the same conditions. So you can certainly work it out in other ways, but if you just think about it logically, we say that helium will effuse 2.25 times faster. That was what we found in the last problem. So however long it takes helium to diffuse, neon should take 2.25 times longer to effuse. If we had been given the time for neon, we divide by 2.25. All right, now it takes 10 seconds for 2 moles of helium to effuse through a certain aperture. If it takes 63.2 seconds for an unknown gas to effuse under the same conditions, what is the molar mass of the gas? Okay, this one is it's a very common one to have in a lab to do this kind of experiment. But it's not as easy to see. We got to think of our rate. The rate is how many atoms or molecules of gas per second that go through. Well, we have moles, so the rate for helium is the amount of gas per time. So they gave us the amount of gas in moles and the amount of time in seconds. So this is not too bad. This is 0.2 moles per second. That's our effusion rate. They could have given it to us in grams or atoms or in volume, but in this case they gave it to us in mole. The rate for the unknown is 2.00 moles for 63, and it takes 63.2 seconds. Notice that the sun, oh, now the sun's back out, good. So the rate is, oops, 0.0316 moles per second. So those are our rates. Now we can put it into our expression. The rate of helium, I'm just going to put rate helium, over the rate of unknown is equal to 0.2 moles per second over 0.0316 moles per second. And that's going to be equal to the rate of helium, so that's going to, the mole is going to be 4.00 grams per mole on the bottom. The unknown is exactly that. It's unknown. We'll call it X. So what we do is 0.2 divided by 0.0316. This is 6.33 is equal to the square root here, but if we take square both sides, we end up with this. save ourselves a little room and a little time. So you square both sides, multiply by 4, and then X comes up to be 160 grams per mole. So we don't know what it is, but we what the unknown gas is, but we certainly know its molar mass. And if we were given a list, say we were told that, oh, and I guess I forgot that I had done this, assuming it is a halogen gas, which halogen is it? I was going to say, I saw that 160, that was very familiar. It's bromine. So in this case, they didn't tell us much more than that, but if we look at the halogens, each of the halogens, there's F2, Cl2, Br2, and I2. The only gas, and bromine is a liquid, but it's a very volatile liquid, and it doesn't say the other conditions here, so if it was hot enough, they'd all be gases, but you see the only gas that has that molar mass is bromine. Okay, then we have 2 questions about real gases. Here. What are 2 differences between real gases and ideal gases? I'll just put RG for real gas. Real gases attract each other and affect pressure that way. So the pressure is lower because when they than it should be, as they come in contact with each other, they actually always attract each other. Real gases have a volume. They aren't point particles. Since they have a volume, have a volume of each molecule, which affects the total, which affects total volume. Another thing that they do, real gases liquefy, we'll say turn into liquids and solids under high pressure and low temperature. Our ideal gases never do. It doesn't matter if we put them under 1,000,000 atmospheres pressure or go down to 0 Kelvin or nearly 0 Kelvin. Our ideal gases are supposed to remain gases. So that obviously is doesn't work out when we get into real conditions of high pressure and low temperature. But as long as we stay within a certain range of temperature and pressure, we're fine. Okay. What is different about the van der Waals equation that allows it to give better results than the ideal gas law? Oh, that's nice. So we have PV equals nRT, and that's the ideal gas law. That was the phone. I'm sitting right next to it. It's wonderful. Well, I've done 20 minutes. I'm sorry. I'm doing the rest of this video. Here's the van der Waals equation. The van der Waals equation is for real gases. And you can see that it's really, if you get rid of this term and this term, we're back to the ideal gas law. So he did something to each the pressure and volume term. This term accounts for intermolecular forces. Attractive forces affect the pressure, as we said above. This term accounts for the volume of molecules. Molecules, even though they're very tiny, they do have a certain amount of volume, and so we have to take that into account. The number of moles times the volume per mole of those gases are subtracted from the total volume. And this is important because the volume, when you take into account the volume of the molecules, well, that's a place that the other molecules can't go. So the volume inside the container is not the full container, it's the full container minus the volume of the rest of the molecules. So each of these terms is important. I don't do anything in my class as far as calculations with this equation, and in lecture I explain that more. But for us, all you really need to know is how is the van der Waals equation different from the ideal gas law?